before the first stars, before the first atoms, before even space and time, there was nothing. Not the silence of an empty room, not the darkness of deep space, but a nothingness beyond imagination. A void without dimension, without duration, without being. And yet, from this abyss, everything was born. Nearly 14 billion years ago, the Big Bang erupted, unleashing energy and matter, time and geometry, galaxies and gravity. But the mystery remains. How could something arise from nothing? How could existence spring from a stage where even the concept of a stage did not exist? To ask what came before the Big Bang is to step outside the limits of language. Before implies time, and time itself began with the birth of the universe. To speak of nothing is to conjure emptiness. But physics suggests that even the void may be filled with hidden potential, a restless sea of quantum possibility. And yet, the paradox is unavoidable. If the universe had a beginning, it must have emerged from something or from nothing. But how can nothing exist? How can it cradle the seed of everything we see, every star, every thought, every dream? This is no question of idle philosophy. It is one of the deepest mysteries science has ever faced. For if we can understand how the universe began, from silence into song, from absence into being, then perhaps we can begin to understand why there is something at all, rather than nothing. The journey begins at the edge of the void, where science and wonder meet. The question of what came before the universe did not trouble ancient astronomers. For millennia, the heavens seemed eternal, the stars steady, the cosmos changeless. Philosophers debated the meaning of infinity, but the sky gave no hint of a beginning. It was not until the 20th century that cracks began to appear in this illusion of permanence, and with them, the first glimpses of a universe that had not always been. The seeds of discovery were planted in the mathematics of Albert Einstein. In 1915, his theory of general relativity reimagined gravity not as a force, but as the bending of space-time itself. The equations, elegant and revolutionary, suggested something unsettling. The universe could not remain static. It must either expand or contract. To Einstein, this was unacceptable. The universe, he believed, was eternal and unchanging. To save his vision, he introduced the cosmological constant, a mathematical device designed to balance the equations, holding the cosmos in place. But the equations were stubborn. They carried within them a whisper that Einstein could not silence. The universe wanted to move. The voice of this whisper grew louder through the work of a Belgian priest and physicist, Georges Lemaire. In 1927, studying Einstein's equations, Lemaire proposed something audacious, that the universe was expanding. If so, then it must once have been smaller, denser, hotter. He imagined all of space and time compressed into a single primeval atom, a cosmic seed from which the universe burst forth. At first, the idea was dismissed. Many clung to the notion of an eternal cosmos. Even Einstein himself reportedly told Lemaire, "Your calculations are correct, but your physics is abominable." Yet the seed of doubt had been planted, waiting for evidence. That evidence arrived not in equations, but in light. In the 1920s, at the Mount Wilson Observatory in California, Edwin Hubble trained the world's most powerful telescope on the spiral nebulae. For centuries, their nature had been debated. Were they clouds within our own galaxy, or entire galaxies themselves? island universes adrift in the dark. Hubble's painstaking observations revealed the truth. The nebulae were galaxies, and they were rushing away from us. Even more shocking was the pattern. The farther a galaxy, the faster it receded. The universe was not static at all. It was expanding, stretching like the surface of a balloon as it inflated. In a single discovery, the eternal cosmos dissolved. The universe had a history, and if it was expanding now, it must once have been smaller, compressed into a state beyond comprehension. The implications were staggering. If galaxies were moving apart, then winding the clock backward meant all matter and energy converged. Space and time themselves must have begun in a singular event, the birth of the universe. Skepticism remained, but the evidence grew. By the 1940s, theorists like George Gamow, Ralph Alpher, and Robert Herman predicted that if the universe began in a hot, dense state, then the afterglow of that fireball should still fill the cosmos. Billions of years later, it would have cooled to a faint microwave radiation, a relic of creation itself. For decades, this remained a bold prediction, untested, almost forgotten. Then, in 1965, chance delivered proof. At Bell Labs in New Jersey, two engineers, Arno Penzias and Robert Wilson, were testing a radio antenna when they detected an unexplained noise, a faint, persistent hiss. They tried everything to remove it, even cleaning out the nests of pigeons roosting in the instrument. But the signal remained. Unbeknownst to them, another group of physicists at Princeton was searching for precisely this radiation. The hiss was the cosmic microwave background, the afterglow of the Big Bang, echoing across space and time. With that discovery, doubt evaporated. The Big Bang was no longer speculation. It was an observation. The universe had indeed been born in fire 13.8 billion years ago from a state of unimaginable density and heat. Yet with every answer came a deeper question. If the universe had a beginning, what came before? If time itself began at the Big Bang, how could before even exist? For the first time, humanity faced the paradox in scientific terms. The cosmos was not eternal. It had emerged, and in its emergence, it forced us to confront the possibility that nothing might not be emptiness at all, but the womb of everything. The discovery phase ended not with certainty, but with wonder, and with a haunting silence that science could not yet explain. The discovery of the cosmic microwave background in 1965 was more than confirmation of the Big Bang. It was a revelation. For the first time, humanity could listen to the faint afterglow of creation, a signal carrying the memory of a universe only a few 100,000 years old. That light, stretched by billions of years of cosmic expansion into invisible microwaves, was proof that the cosmos had indeed been born in fire. But science does not rest on singular proofs. The background radiation was soon studied with greater precision, and each new observation deepened the story. In the early 1990s, the COBE satellite, Cosmic Background Explorer, mapped the radiation in detail. It revealed not uniformity, but slight ripples, fluctuations in temperature no greater than 1 part in 100,000. These tiny variations were seeds, destined to grow into galaxies, clusters, and the vast structures of the modern universe. In the ripples of ancient light lay the blueprint of everything. Later missions, WMAP Wilkinson Microwave Anisotropy Probe in 2001 and Planck in 2009, refined the map with exquisite precision, confirming predictions of the Big Bang with astonishing accuracy. They measured the age of the universe at 13.8 billion years, confirmed the dominance of dark matter and dark energy, and cemented the picture of a cosmos that had once been dense, hot, and rapidly expanding. Yet, with every layer of confirmation came deeper mysteries. The Big Bang Theory explained much, but not everything. It described the universe after its first fractions of a second, but what of the moment itself? What of the nothingness before? To address this, physicists turned to the processes thought to have occurred in the universe's earliest instance. Among them was nucleosynthesis, the formation of light elements. Gamow, Alpher, and Herman had predicted that the Big Bang should have forged hydrogen, helium, and traces of lithium in precise ratios. Observations of the cosmos matched these predictions almost perfectly, further anchoring the theory. But again, the evidence sharpened the paradox. If the Big Bang explained what happened after the beginning, it still did not explain the beginning itself. The equations of general relativity, when wound backward, collapsed into a singularity, a point of infinite density and zero volume where the laws of physics broke down. Beyond that singularity, the equations were silent. To speak of before the Big Bang was to step into a realm without time, without space, without physics as we knew it. The discovery phase thus evolved into a paradoxical state. The more evidence accumulated for the Big Bang, the more haunting became the question of origins. The universe had begun, but what had given it birth? In the late 20th century, a new idea emerged to fill some of these gaps: cosmic inflation. Proposed by Alan Guth in 1980, inflation suggested that in the universe's first trillionth of a second, space itself expanded faster than the speed of light. This brief, violent burst of expansion smoothed the cosmos, explained the uniformity of the microwave background, and seeded the tiny fluctuations that would grow into galaxies. Inflation was powerful, elegant, and supported by the data. But it raised a deeper mystery still. What caused inflation? What field or force drove this unimaginable expansion? And if inflation ended to give rise to our universe, might it continue elsewhere, spawning countless other universes? The deeper the evidence ran, the sharper the question of nothing became. If inflation were real, then what existed before inflation? If a singularity was not the ultimate truth, then what lay beyond it? Scientists stood on the threshold of the void, armed with equations and satellites, yet unable to pierce the veil. For the public, the story seemed simple. The universe began with the Big Bang. But for physicists, the discoveries were unsettling. Each proof of the Big Bang was also a reminder that the ultimate question remained unanswered. How could nothing give rise to everything? Thus, the discovery phase closed with a paradox. The Big Bang was no longer speculation, but fact. The universe had a beginning. And yet, that very beginning forced science to confront a mystery more profound than ever: the existence of nothingness itself. The confirmation of the Big Bang brought with it not triumph alone, but unease. For if the universe truly had a beginning, then physics had to explain not just how the cosmos evolved, but how it came to be. This was the moment when science, triumphant in its discovery, stumbled upon a paradox it was not prepared to face. At the heart of the paradox lay the singularity, that mathematical point where the equations of general relativity, when wound backward in time, describe the universe compressed to infinite density and zero volume. Space and time themselves collapsed into nothingness. It was a limit not just of matter, but of knowledge. At t equals 0, the fabric of physics itself unraveled. For centuries, Humanity had taken comfort in the notion of an eternal cosmos. The ancients imagined it as unchanging, infinite, stretching backward forever. Even Einstein, in his first attempts at cosmology, resisted the idea of a universe with a beginning. Now, the evidence had turned inexorably against eternity. The cosmos had not always been. It had been born. The shock was existential. If the universe had a beginning, then what of the laws of nature that governed it? Did they exist before time, waiting like hidden instructions in the void? Or did they emerge only as the universe was born, carried in the first expansion, like a melody in its first note? General relativity, powerful as it was, offered no comfort. Its equations broke down at the singularity, yielding infinities that no physicist could accept as reality. Time could not be wound further back. The theory itself fell silent. This was not science as it had been known. This was a confrontation with the edge of understanding. Into this silence stepped quantum mechanics, the other great pillar of modern physics. But it too faltered. The uncertainty principle allowed for fluctuations, for the spontaneous birth of particles in a vacuum. Yet at the singularity, where space and time themselves dissolved, quantum mechanics lost its footing. Without a stage, probabilities could not play. Without time, evolution had no meaning. The tools of physics, sharpened through centuries, were useless at the very moment they were most needed. The scientific community reeled. The discovery of a beginning, confirmed by expanding galaxies and ancient light, was no longer a triumph. It was a crisis. Science had revealed the origin of the universe, only to discover that its own laws could not cross the threshold. The philosophical weight of this shock was immense. For to say that the universe had a beginning was to ask what came before. But if time itself was born with the Big Bang, then before was meaningless. Human language, human thought, even human imagination strained at the paradox. How could nothing precede everything? How could time begin when time is needed to measure beginnings? The shock was not confined to physics. It echoed into philosophy, theology, and culture. To some, the Big Bang sounded like creation itself, an echo of ancient myths that spoke of beginnings in fire and light. To others, it was a threat, a scientific explanation of origins that left no room for divine eternity. For the physicists caught in the storm, the tension was sharper. Their equations had described the universe with unparalleled accuracy, yet here they failed at the most fundamental question of all. The scientific shock was thus twofold. First, that the universe had a beginning. Second, that physics itself collapsed at that beginning. The twin pillars of relativity and quantum mechanics, each so powerful in its domain, stood opposed, unable to merge into a theory that could explain the birth of everything. Some sought refuge in speculation. Perhaps the singularity was not real, but a signpost of incomplete understanding. Perhaps the true beginning lay hidden behind new mathematics yet to be discovered. But these were hopes, not answers. The weight of the paradox was crushing. Scientists who had expected triumph found themselves staring into a void deeper than any they had imagined. For the question was no longer how the universe worked, but how it could exist at all. The shock of discovery had given way to the shock of ignorance, and in that silence, a new urgency was born to go beyond Einstein, beyond quantum mechanics, beyond the limits of science itself, in search of an answer to the most haunting question of all. How did nothing give rise to everything? The singularity was more than a mathematical inconvenience. It was a philosophical earthquake. If the universe truly began at a singular point, then physics itself was telling humanity that there was a boundary to knowledge, a wall beyond which no theory could see. For scientists, this was not merely frustrating, it was terrifying. The terror deepened in the 1960s and 1970s when Stephen Hawking and Roger Penrose sharpened Einstein's equations into rigorous theorems. Their singularity theorems showed that under general conditions, the collapse of matter or the expansion of the cosmos inevitably led to singularities. These were not rare accidents in the equations, they were unavoidable. If relativity were correct, then the universe truly began at a point where density was infinite and time itself ceased to exist. The shock was total. Relativity, the theory that had explained black holes, the bending of light, and the expansion of the cosmos, now pointed to its own destruction. At the beginning, it broke. Quantum mechanics, meanwhile, offered little refuge. The uncertainty principle allowed for the creation of particles out of vacuum fluctuations. But such phenomena still required a stage on which to occur. At the singularity, where time and space collapsed, there was no such stage. Without dimensions, probability itself was meaningless. The clash between relativity and quantum theory grew sharper. Each was a monument of human genius, tested by experiment and proven true in its domain. Yet at the origin of the universe, they stood opposed. Relativity demanded a singularity. Quantum theory denied its possibility. The universe, it seemed, could not exist without tearing its laws apart. This contradiction produced a sense of intellectual vertigo. Scientists, who had grown accustomed to physics as a path toward deeper certainty, now confronted the possibility that the cosmos itself was inconsistent. How could the universe exist if its governing laws could not agree on its origin? The implications reached beyond laboratories. In philosophy and culture, the Big Bang was interpreted as proof of creation, a scientific echo of ancient myths of beginnings. Some theologians seized upon it as validation of their traditions. Others feared that science had invaded sacred ground. Yet for physicists themselves, the problem was neither theological nor ideological. It was existential. If their equations could not explain the beginning, then the very foundation of science was at risk. The paradox also transformed the scientific imagination. Before the confirmation of the Big Bang, cosmology had been considered speculative, even peripheral to physics. Afterward, it became central. The question of origins was no longer a philosophical abstraction, it was the sharp edge where relativity and quantum mechanics collided. Physicists who once built accelerators to probe particles have now turned their eyes to the heavens, seeking clues to the first moments of existence. The sense of crisis was heightened by the sheer scope of the question. To ask what existed before the Big Bang was to challenge the meaning of before. If time itself were born with the universe, then before had no meaning. Yet the human mind rebelled against this logic. We are creatures of causality, of sequence. To say there was no time before time was to confront a reality beyond comprehension. The shock became a kind of intellectual wound. Each new discovery, the expansion of galaxies, the microwave background, the precision of nucleosynthesis, pressed deeper into it. Evidence mounted for the Big Bang. Yet with every confirmation came the reminder that physics could not explain its beginning. Hawking himself wrestled with this paradox throughout his career. At first, he accepted the singularity acknowledging the breakdown of physics at the origin. Later, with James Hartle, he proposed the no-boundary model, an attempt to describe the early universe without a singular beginning. Yet even this bold speculation underscored the depth of the crisis. To avoid the paradox, new physics was required, beyond the reach of relativity or quantum theory alone. By the late 20th century, the scientific shock had matured into a global challenge. It was no longer possible to dismiss the paradox as a philosophical curiosity. It had become the central problem of cosmology, the riddle that demanded unification of all physics. And so, what began as triumph, the discovery of the Big Bang, became the source of the greatest scientific unease of the modern age. The cosmos had revealed its beginning, only to show that the beginning was a place where knowledge itself dissolved. The scientific shock of the Big Bang was not the realization that the universe began. It was the realization that science, as it stood, could not explain that beginning. The most powerful theories of human history, the monuments of Einstein and Bohr, faltered at the threshold of creation. And in that faltering, the mystery of nothingness grew darker, heavier, and more profound. The shock of the singularity left physics standing at a cliff edge, staring into the abyss of nothingness. Yet scientists did not retreat. If relativity and quantum mechanics collapsed at the beginning, then perhaps the path forward lay not in surrender, but in unification. The deeper investigation began, a search for new principles that could carry the human mind where old theories failed. One of the first great attempts came from Stephen Hawking and James Hartle in the early 1980s. They proposed the no-boundary model, a daring idea that sought to dissolve the singularity itself. In their vision, time did not begin as a sharp edge, a boundary at t=0. Instead, time curved smoothly, like the rounded surface of the Earth. Just as one cannot fall off the edge of the globe, for the globe has no edge, the universe had no first moment. It emerged smoothly, without singularity, from a quantum state where time itself was blended with space. The mathematics was abstract, but its message was clear. Asking what came before the Big Bang was like asking what lies north of the North Pole. The question itself lost meaning. In this way, the no-boundary proposal sought to silence the paradox, not by answering it, but by dissolving it. Others turned to the restless energy of the quantum vacuum. In quantum theory, the vacuum is never truly empty. Even in nothing, particles flicker into and out of existence, borrowing energy from uncertainty, vanishing again in moments too brief to observe. Some physicists speculated that the universe itself might have arisen from such a fluctuation, that a tiny bubble of energy, born from nothing, expanded into the cosmos we see today. This vision reframed the paradox. Nothingness, in the language of quantum mechanics, was not absence but potential. The void was a sea of possibilities, restless with fluctuations. From it, universes might bloom like foam on a cosmic ocean. The concept of inflation, proposed by Alan Guth, gave this speculation greater power. Inflation suggested that in the universe's earliest fraction of a second, space itself expanded at unimaginable speed. This expansion smoothed the cosmos and explained the uniformity of the microwave background. But inflation also hinted at something deeper, that perhaps inflation never fully ends. In some regions, bubbles stop inflating, forming universes like ours. In others, inflation continues, spawning countless universes in a vast multiverse. If so, then our universe may not be the only one, merely one bubble among many, born from the quantum foam of nothingness. And the nothing before our Big Bang might not have been a singular void, but an infinite process of creation, birthing cosmos after cosmos. Still, the investigation revealed contradictions as well as possibilities. Quantum fluctuations might explain how a universe could appear, but they did not explain why the laws of physics were already present to govern them. The no-boundary proposal dissolved the question of before, but it left unanswered the deeper puzzle. Why should existence be possible at all? Yet the pursuit continued, weaving through mathematics and speculation. Physicists began to construct models of the earliest universe, seeking to merge relativity and quantum mechanics into a single theory of quantum gravity. String theory and loop quantum gravity each offered glimpses of a framework where space-time itself was emergent, where singularities might vanish, and where the void itself could give birth to worlds. The deeper the investigation went, the more the word nothing lost its simplicity. Nothingness was not empty. It was structure unseen, potential unrealized, laws unexpressed. To speak of nothing was to speak of the hidden foundation upon which something could arise. And in this shift, the paradox deepened. The more science studied nothing, the more it looked like something. The void shimmered with energy, with possibility, with law. Perhaps nothing had never truly existed at all. The investigation had not resolved the mystery. It had transformed it. The paradox of nothing refused to fade. Each new attempt to explain the beginning of the universe revealed not emptiness, but hidden depth. As physicists pushed further, the void itself seemed to unravel into new layers of meaning, a canvas not blank, but filled with unseen possibility. One of the boldest explorations came through string theory, a framework that reimagined the building blocks of reality not as particles, but as tiny vibrating strings of energy. These strings, existing in multiple unseen dimensions, offered the hope of uniting quantum mechanics with gravity. Within this strange geometry, singularities could be softened, horizons smoothed, and the question of beginnings reframed. The Big Bang, in some string-inspired models, was not the start of time itself, but a transition, a bounce from a previous state or a collision of higher dimensional brains in a hidden space. This led to the idea of the ekpyrotic universe, a model in which our Big Bang was triggered by the collision of vast membranes floating in higher dimensions. In this vision, nothing before the Big Bang was not emptiness, but silence before impact, a prelude to collision that ignited our cosmos. Time, in such a scenario, did not begin with the bang. It stretched before, carrying cycles of collapse and rebirth across eons unimaginable. Others turned to loop quantum gravity, an attempt to quantize spacetime itself into discrete loops. In this framework, the singularity dissolved into a quantum bounce. The universe, contracting in a previous phase, rebounded instead of collapsing to nothing. Our Big Bang, then, was not a beginning, but a rebirth. The nothing before it was not void, but a prior cosmos, shattered and transformed into ours. These explorations carried profound implications. If the universe were cyclic, then before the Big Bang might have meaning after all. It might refer to a previous universe, collapsed and reborn, leaving faint imprints in our cosmos like echoes in a new song. Scientists searched for such signatures, anomalies in the cosmic microwave background, traces of patterns older than our universe. Some claimed to see hints, though none were decisive. At the same time, the quantum vacuum remained a fertile ground for speculation. The vacuum, seething with virtual particles, fluctuations, and hidden energy, looked less like nothing than like the womb of creation. In quantum cosmology, universes could tunnel into existence spontaneously, born not from emptiness, but from potential. In such models, the void was never void. It was the seedbed of infinite possibility. Yet each attempt to tame the paradox led to deeper questions. If our universe emerged from a vacuum fluctuation, what defined the vacuum itself? If our cosmos were born from brane collisions, what determined the higher dimensional arena in which those branes existed? If time extended through cycles, what was the origin of the cycles themselves? In each case, nothing receded like a horizon. Just as the universe expands faster than we can chase it, the true nature of nothingness always seemed beyond reach. But in this pursuit, physics achieved something profound. It showed that the question of nothing was not a dead end. It was a doorway. The void was not a blank absence, but a frontier of hidden structure, where laws, geometry, and possibility existed before matter, before light, before time. The deeper investigation revealed a paradox that was both humbling and inspiring. The closer science came to describing nothing, the more it resembled something. Emptiness became potential. Silence became structure. Nothingness itself seemed to whisper with the possibility of worlds. Thus, what had begun as shock and silence evolved into exploration and imagination. The Big Bang was no longer the ultimate wall of knowledge, but a threshold, a veil through which physicists glimpsed the outlines of deeper truths. And still, the question lingered, unresolved. What, if anything, lies beyond that veil? The deeper science pressed into the mystery of beginnings, the stranger and more unsettling the answers became. What had started as a search for the origin of the Big Bang now began to look like an unraveling of reality itself. For the closer one looked at nothing, the more it became a mirror that reflected not emptiness, but infinite possibility. The theory of cosmic inflation, so successful in explaining the smoothness of the cosmos, revealed an even darker implication. In its earliest form, inflation was thought to be a brief, fleeting burst, a trillionth of a second, no more. But as the mathematics matured, physicists realized inflation may never truly end. Instead, it might continue eternally in distant regions, creating an endless series of expanding bubbles. Each bubble could become its own universe, with its own laws of physics, its own galaxies, its own story. If this were true, then our Big Bang would not be unique. It was one among countless others, one note in an eternal symphony of creation. The nothing before our universe was not a void at all, but an infinite landscape of potential, spawning cosmos after cosmos without beginning or end. This realization deepened the paradox. For if the universe was born out of eternal inflation, then what, if anything, defined the inflationary field itself? What was the origin of the mechanism that drove creation without pause? The answer receded, horizon-like, every time it was approached. Some physicists proposed that the vacuum itself might not be stable. The cosmos, they suggested, may be living in a false vacuum, a precarious state of energy, like a ball resting in a shallow valley, waiting to roll into a deeper one. If this is true, then a bubble of true vacuum could appear at any moment, expanding at the speed of light and annihilating everything we know. The end of time could arrive without warning, born not of stars or entropy, but of the fragility of the vacuum itself. In this vision, the nothing before creation was not only mysterious, but dangerous. It carried within it the possibility of endings as well as beginnings. Just as the void could give rise to worlds, it could swallow them too. The escalation was not limited to equations. It seeped into the philosophy of existence itself. If universes are born endlessly, then what does it mean to live in one? If nothingness is the mother of infinite creation, then why this universe, here, now? The principle of cosmic selection emerged. Perhaps we inhabit this universe simply because it permits life. Countless others may exist, sterile and silent, but we could never observe them. Our cosmos, then, is not special. It is survivable. For many, this was unsettling. Humanity had long sought to see itself as central, its universe as singular, but the inflationary multiverse stripped away that comfort. If it is true, then our universe is not chosen but random, a single flicker in an eternal blaze. The mystery deepened further with quantum mechanics. The strange logic of quantum theory suggested that not only the cosmos, but reality itself might be branching endlessly. Each choice, each fluctuation, each quantum event could create new paths, new realities, new universes. In such a vision, nothing was not absence, but an infinite fountain of possibilities, forever branching, forever unfolding. The escalation of the paradox weighed heavily. What had begun as a question about a singular beginning had expanded into visions of infinity, multiverses, false vacuums, eternal inflation, endless quantum branching. The more science sought the origin of everything, the more it revealed a reality where origins themselves dissolved. And in this dissolution lay the deepest terror of all, that the question, what came before, might have no answer, that nothing was never truly empty, and that the beginning of our universe was only a moment in an eternal cycle with no ultimate origin. Yet, alongside terror, there was awe. These visions expanded the scope of imagination to scales never before conceived. To live in a universe that is one among many, to exist within a cosmos that may be unstable, to ask questions of beginnings that may never be resolved, this is to live at the edge of human thought. The escalation was not the end of the story, but the deepening of it. Nothingness was no longer silence, it was storm. The more scientists pressed into the abyss of origins, the more the mystery of nothing seemed to rebel against definition. What had once appeared as a simple paradox, how could something arise from nothing, now unfolded into an escalating storm of theories, each stranger, more unsettling, and more audacious than the last. At the heart of this escalation was the realization that physics itself might be unstable. The idea of a false vacuum, a universe perched precariously on a shallow plateau of energy, hinted at a cosmos built not on permanence, but fragility. Like a glass resting on the edge of a table, reality could at any moment tip into oblivion. A bubble of true vacuum could emerge, its expansion devouring galaxies, stars, and atoms at the speed of light. To ask about the nothing before the Big Bang now also meant to confront the possibility of the nothing that might follow, a silence more absolute than any beginning. This prospect was not a fantasy, but a consequence. Quantum field theory allowed for metastable vacuums, states that endure for billions of years, yet are not eternal. Our universe, it seemed, might be such a fragile oasis, destined to vanish into a deeper void. Nothingness was no longer a philosophical abstraction. It was a future, lurking like an invisible horizon. And yet, the same mathematics that threatened doom also promised infinity. Inflation, once a brief flash, became in some models an eternal process. New universes budded endlessly, each one expanding into its own horizon. If one collapsed, countless others bloomed. In this eternal inflation, the void was not empty, but fertile, a womb of universes stretching without beginning or end. For some, this was a liberation. The question, what came before, could be reframed. If universes were born without end, then there was no single beginning. Our Big Bang was not the moment of creation, but a moment in an infinite process. Nothing became an illusion, a word used only because we could not see beyond the horizon of our own cosmos. But for others, the vision was unbearable. An eternal multiverse dissolved not just origins, but meaning. If universes arose without limit, then every possibility existed somewhere, countless times over. The laws of physics that seemed so constant in our cosmos might vary in another. The very idea of necessity unraveled. Why this universe? Why these laws? Why us? Perhaps there was no answer. Perhaps there could never be. This was the principle of anthropic selection. Whispered first as speculation, later as reluctant conclusion. We find ourselves in a universe not because it is unique, but because it is survivable. Among infinite possibilities, only those hospitable to life can be observed. Our cosmos, then, is not chosen, not ordained. It is merely tolerated. To many, this stripped the question of its grandeur. To others, it revealed a haunting beauty. That life itself was a rare flame flickering against the endless wind of creation. Yet even as inflation and multiverse theories grew, deeper currents unsettled the surface. String theory, with its vast landscape of possible universes, suggested that countless vacuum states could exist, each with its own physics. Our universe might be one solution among 10 to the 500 possibilities, an incomprehensible library of realities. If true, then nothing was not void, but abundance beyond measure. And still, the origin of the library remained hidden. Who, or what, wrote the code that allowed so many realities to bloom? Quantum mechanics, too, refused to yield simplicity. The multiverse of inflation was joined by the multiverse of measurement, the many worlds interpretation. Every quantum decision, every branching of probability was said to split reality into countless paths. If so, then universes multiplied not just in inflationary bubbles, but at every instant, with every particle. Nothing became even harder to define. Which nothing? Which universe? Which branch? The escalation of paradox was dizzying. From singularity to inflation, from false vacuum to multiverse, from string landscapes to quantum branching, the question of nothing had become a labyrinth. Each turn dissolved certainty and revealed corridors stretching further still. The scientists who entered this labyrinth did so with equations, with satellites, with telescopes aimed at the afterglow of creation. But the further they went, the more it seemed that the void itself was infinite, an abyss with no bottom, only horizons upon horizons. And yet, through this vertigo, awe persisted. The escalation did not erase wonder, it deepened it. To live in a universe perched on a fragile vacuum, to exist in one bubble among infinite others, to branch across quantum possibilities, this was no defeat, it was an expansion. Human imagination, once confined to a single eternal cosmos, now ranged across infinities. Science, pressed by paradox, had not shrunk the mystery of nothing, it had magnified it. Still, the danger was real. If our vacuum is false, then a true vacuum collapse could erase us in an instant. If inflation is eternal, then our universe is temporary. one among countless. If string theory is correct, then the laws we cherish are but local dialects in a cosmic babel. And if quantum branching is true, then reality itself is fractured beyond recognition. In each vision, the origin slits away. Nothing becomes a horizon receding faster than light, a mystery deepening each time it is approached. But perhaps that is the final lesson. Perhaps the paradox is not to be solved, but to be lived with, a reminder that the universe we inhabit is stranger than we can conceive, and that the question of nothing may always remain just beyond reach. The escalation of the mystery transformed the question of origins into something more profound. It was no longer about beginnings alone. It was about fragility, infinity, and possibility. It was about a universe in which nothing was ever truly empty, and everything was never truly secure. It was about existence itself, trembling on the edge of the void. And so science, born in the triumph of discovery, now stood at the edge of humility. For the deeper it probed into nothingness, the more it revealed not answers, but questions. Questions that would define not only cosmology, but philosophy and the human imagination itself. The paradox of nothingness could not be left to silence. With the shock of the singularity still echoing, physicists began to weave new theories, daring speculations that might pierce the veil. If relativity and quantum mechanics faltered at the threshold, perhaps new principles could be found beyond them, principles strange enough to describe a universe born from nothing. One of the first bold steps came from the restless landscape of quantum mechanics itself. In the world of the very small, emptiness is never truly empty. What we call the vacuum is not a barren void, but a sea of fluctuations, where particles flicker in and out of existence, borrowing energy from uncertainty before vanishing again. Physicists began to wonder, could the universe itself be one such fluctuation? Could the cosmos be a bubble of space-time, born spontaneously from the quantum vacuum? The idea seemed outrageous, yet the mathematics allowed for it. In quantum field theory, probabilities rule where certainties fail. A universe, it was argued, could tunnel into existence in the same way that particles emerge from the void. From nothing, if nothing is understood as quantum potential, something could be born. In this vision, the Big Bang was not an absolute beginning, but the most extraordinary quantum fluctuation of all. But what of relativity? Einstein's equations, so elegant in describing the bending of spacetime, collapsed at the singularity. Yet even within relativity lay hints of escape. Some physicists proposed that the singularity was not a real point, but an artifact, a sign that the theory itself was incomplete. Perhaps the Big Bang was not the edge of time, but a transition, a bounce from a prior state. This idea gained momentum in the form of loop quantum gravity. By treating spacetime itself as quantized, woven from discrete loops, the theory suggested that singularities might be smoothed away. Instead of collapsing into infinite density, a prior universe might have rebounded, giving birth to ours. In this cyclical vision, the nothing before the Big Bang was not absence, but another cosmos, shattered and remade. String theory offered another path, reimagining particles not as points, but as tiny vibrating strings of energy. Within its vast mathematics lay the possibility of higher dimensions, unseen but real. Some theorists imagined our universe as a three-dimensional brain, floating in a higher dimensional space. In this framework, the Big Bang might have been the collision of such brains, titanic membranes slamming together, igniting a new cosmos in the aftermath. Nothingness, in this story, was not void, but the quiet tension of hidden dimensions waiting to collide. Even more radical was the speculation of Alan Guth's cosmic inflation. Inflation explained why the universe is smooth on large scales, why galaxies formed as they did, and why the cosmic microwave background is uniform. But its implications were staggering. If inflation were real, it might be eternal. New universes might bud off endlessly, each one inflating into its own cosmos. Our Big Bang, then, was just one blossom in an eternal cosmic garden. Before our beginning lay countless other beginnings, each born from a restless inflationary field that never ends. Yet, each of these theories, daring though they were, carried its own paradox. If the universe were a quantum fluctuation, what defined the vacuum that allowed it? If it were a bounce, what set the stage for the prior universe? If brain collisions birthed our cosmos, what created the brains themselves? If inflation is eternal, what gave rise to the inflationary field? In every case, the question receded. Nothingness remained elusive, a horizon that retreated each time it was pursued. Still, the speculations were not futile. Each reframed the mystery in ways that expanded human imagination. The no-boundary proposal of Hawking and Hartle, which treated time as curved rather than linear, suggested that before the Big Bang might be a meaningless phrase. Just as one cannot travel north of the North Pole, one cannot travel to a time before time. In this vision, the paradox dissolved, not through explanation, but through redefinition. Nothingness was simply the wrong question. Other physicists leaned into the strangeness of quantum cosmology. Alexander Vilenkin proposed that the universe could arise from nothing through quantum tunneling, a process akin to particles escaping barriers in the subatomic world. In his vision, even if absolute nothingness existed, no space, no time, no laws, quantum probability could still allow for the spontaneous birth of a universe. Creation, in this model, did not require a cause. It required only possibility. The shock of these ideas was not their mathematics alone, but their implications. If universes can be born from quantum foam, then creation is not unique. If time curves smoothly into itself, then beginnings dissolve into geometry. If inflation buds eternally, then nothingness is never empty, but always pregnant with potential. To skeptics, these speculations seemed like philosophy disguised as physics. To believers, they were the first glimmers of a deeper truth. The pursuit of nothing had become a pursuit of everything, of laws, structures, and possibilities hidden beyond the reach of observation. What unified them all was a refusal to accept silence. Physics could not ignore the paradox. It could not rest at the edge of singularity. With every tool at its disposal, from quantum uncertainty to higher dimensions, from inflationary fields to mathematical tunneling, it sought to peer beyond the veil. Yet the veil remained. Theories multiplied, but certainty did not. Each new vision deepened the mystery, making nothing seem less like emptiness and more like a secret architecture, a hidden stage upon which existence could be born. And so the paradox grew sharper. If nothing was unstable, then perhaps it was never real. If universes can bloom eternally, then perhaps beginning is an illusion. If time is curved, then perhaps causality itself dissolves. Theories and speculations expanded the question, but they did not end it. For science had discovered a truth as unsettling as it was profound. The closer it came to describing nothing, the more it resembled something. Theories multiplied like constellations, each a shard of light cast into the dark. No single model could silence the question, yet together they sketched an outline of possibility, a cartography of the unknown. And always, at the center, the same riddle. What does nothing mean when the universe itself is allowed to speak? Some physicists turned their gaze to a familiar constant that had once been introduced to halt a restless cosmos: the cosmological constant. In Einstein's hands, it was a balancing weight. In modern physics, it became a whisper of something deeper: dark energy, the pressure that drives the expansion to accelerate. If the vacuum carries energy, if emptiness has weight, then nothingness is not empty at all. It is an ocean with surface tension. A field whose faint push can fling galaxies apart. In this view, the nothing before creation might be a landscape of vacuum energies, some high, some low, with universes budding where conditions allow. The cosmological constant ceases to be a number. It becomes a selection, a lottery ticket drawn from a vast and silent urn. Others tried to tame beginnings with the asymptotes of renormalization. Asymptotic safety, a program in which gravity might become well-behaved at the highest energies, offered a hope that the singularity was an illusion born of extrapolation. If the strength of gravity runs to a fixed point as energies climb, then the Big Bang may not be a tear in the fabric, but a tight weave too small for classical eyes to resolve. Nothing shrinks here into the grain of space-time. Not the absence of thread, but the limit of our loom. A different thread imagined the universe as a computation in stone. Not metaphor, but discreteness. In causal set theory and related approaches, space-time is not continuous. It is a sprinkling of events, atoms of geometry linked by cause. There is no smooth surface to rip. At the smallest scales, there is only a web of precedence. This before that before another. A beginning becomes not a boundary, but the first click in an endless chain. A primordial relation from which the entire tapestry unfurls. Nothingness in such a world is not a void to be filled. It is the absence of relations, the silence before the first happened. The most audacious speculations leaned into emergence itself. Perhaps space-time is not fundamental. Perhaps it condenses from more primitive degrees of freedom, entanglement, knitting geometry, information sewing distance, temperature setting curvature. In these ideas, born from the marriage of quantum theory with hints from black hole thermodynamics, the line between something and nothing blurs further still. If geometry emerges from entanglement, then before space is before correlation. Nothingness would be a state without links, a pure disconnection. Creation, then, is the onset of relation, the sudden appearance of networks binding once isolated quanta into a shape we learn to call space and a flow we learn to call time. There were cycles that refused finality. Conformal cyclic cosmology imagined aeons, entire universes expanding into thinness until mass lost its meaning and only light remained. In that traceless future, the far edge of time could be squeezed by a mathematical transformation into a new beginning. One universe's cold eternity became another's hot dawn, without a singular tier between. Nothingness became the quiet match between extremes, the vanishing of mass at one end, the smothering of scale at the other. There were bounces that rejected collapse. In loop quantum cosmology, quantum geometry stiffened spacetime against infinite compression. Density reached a universal ceiling, gravity's pull inverted, contraction rebounded. On that rebound, a new expansion rose. Nothingness became a misreading, not an abyss, but a turning point, written in the algebra of area and volume. There were brains that collided, landscapes that sprawled, and vacua that tunneled. There were models in which universes nucleated like bubbles in a boiling pot of possibility, each new cosmos sealed by its own horizon. There were accounts in which geometry itself was a hydrodynamic limit, the way a fluid emerges from molecules, smooth at a distance, granular underneath. In each, the story of the beginning wore a different mask, yet all masks shared the same face. That emptiness could carry structure, that silence could hum with law. The paradox, however, did not loosen its grip. Every theory that replaced nothing with something, vacuum energy, entanglement networks, discrete causal sets, higher dimensional brains, answered the mechanics of a birth while dodging the ontology of a void. If nothing contains fields, relations, or rules, then in what sense is it nothing? And if nothing is truly empty, no space, no time, no law, how can possibility itself survive that absence? Probability cannot float without a measure. Equations cannot speak without a language. The mind walks to the precipice and finds not a wall, but mist. Some embraced the anthropic turn with reluctance and with rigor. If the landscape of possible universes is immense, and if only a thin slice of that landscape permits chemistry, stars, and observers, then perhaps the smallness of the cosmological constant, the heaviness of the Higgs, and the balance of forces are not deep necessities, but environmental facts. We are here because in most places, one cannot be. This answer preserves physics at the cost of inevitability. It explains by diluting. For those who need a single law to anchor meaning, the multiverse is a cruel gift. For those who accept selection, it is an end to the question, why these numbers? And the beginning of why anything that selects at all. At the edge of speculation waited a darker anxiety. Boltzmann brains, minds spontaneously fluctuated from chaos in rare far futures, raising fears that typical observers might be deluded by minimal worlds. The cure for such nightmares, many argued, is dynamical, a cosmology in which such freak observers are vanishingly improbable. Yet the anxiety shows the reach of the paradox. When we press emptiness too hard, it answers with strange nearers. Even the language of time was forced to change. If a beginning is a boundary in a parameter we call t, then asking what came before is as misguided as asking for the color of temperature. But if time is emergent, a coarse-grained flow distilled from deeper, timeless microdynamics, then beginnings are phase transitions, not edges. The universe does not appear from nothing. It condenses from the formless into the formed. The image shifts from explosion to crystallization. Asymmetry breaks, degrees of freedom pick a direction, and history starts to count itself. In this forest of ideas, two compass needles refused to budge. The first was consistency. Any story must respect what is already measured. The success of general relativity on cosmic scales, the quantum rules that govern particles, the fossil light of the cosmic microwave background, the abundances of light elements, and the late-time acceleration. The second was testability. A theory that explains everything, explains nothing. Speculations are not ends. They are bridges to predictions. Can a cyclic bounce leave scars in the sky? Can emergent geometry imprint non-Gaussian whispers in the microwave afterglow? Can vacuum instability be cornered by the masses we measure and the couplings we refine? Even in the realm of nothing, science refuses to float free of evidence. And yet, for all the discipline, the mood remained chastened, almost reverent. Theories and speculations do not so much conquer the void as teach us how to stand before it. They show that the question, "How did nothing exist?" might be a request to translate our intuitions into a grammar the universe does not speak. Perhaps there was never anything in the human sense. There were only states we cannot picture, rules we can only infer, and transitions we can only name by metaphor. So the catalog remains provisional, like a night sky seen through thin cloud. Here a bounce, there a brain, beyond a landscape, beneath a lattice, above a constant that is not constant at all. Between them runs a single theme, that what we call nothing may be the most structured thing we will ever fail to see. And still the question glows, patient and inexhaustible. It is the ember that keeps cosmology warm, not to banish mystery, but to refine it. Not to draw a border around the beginning, but to learn how beginnings arise from laws that never start. In that quiet ambition lies the strange dignity of the search. The universe could have been silent. Instead, it gave us just enough echo to wonder. The paradox of nothingness had carried physics to the very edge of imagination. Yet speculation alone could not hold the weight of science. To ask how the universe began, or whether nothing could truly exist, demanded not only mathematics, but observation, instruments sharp enough to pierce the afterglow of creation, telescopes vast enough to map the heavens, and detectors sensitive enough to feel the tremor of space-time itself. The deeper the question grew, the more urgent became the search for tools that could test the fabric of beginnings. The first great tool was light itself, or rather, its oldest memory. The cosmic microwave background had already shattered the illusion of an eternal universe, revealing the universe's infancy as a sea of hot plasma, cooling into structure. But its faint ripples contained more than confirmation. They contained prophecy. Satellites like COBE, WMAP, and Planck became time machines, mapping temperature variations with exquisite detail, transforming ancient radiation into a cartography of origins. Planck's data, released in 2013, refined the age of the cosmos to 13.8 billion years and showed the fingerprint of inflation itself. The subtle distribution of ripples across the sky matched predictions that the early universe had expanded at extraordinary speed. If inflation were true, then perhaps the seeds of the multiverse lay hidden in the geometry of the microwave sky. The first whispers of speculation had become testable patterns, written not in ink, but in photons older than the first stars. Yet telescopes alone could not shoulder the weight. The paradox of nothingness was a collision of gravity and quantum mechanics, and to test it required hearing space-time itself. In 2015, humanity did. At twin observatories in Louisiana and Washington, the Laser Interferometer Gravitational Wave Observatory, LIGO, caught the tremor of colliding black holes. For the first time, space-time was not inferred, but heard, its ripples ringing through the detectors with the precision of a cosmic bell. Gravitational waves offered a new sense, a new language of the universe. If the early universe had indeed passed through inflation, it must have sent a background of primordial gravitational waves rolling across the cosmos. Detecting them would be like hearing the heartbeat of creation itself. Instruments like LISA, a planned space-based observatory, and pulsar timing arrays already searching for low-frequency signals, are designed to listen for that faint rhythm. If found, they would not only confirm inflation, but reveal the energy scales at which nothingness itself boiled into something. On another front, particle accelerators tried to recreate the conditions of the early cosmos. At CERN's Large Hadron Collider, protons collide at nearly the speed of light, unleashing energies unseen since the first trillionths of a second. These collisions are not mere fireworks. They are keys to the vacuum. The discovery of the Higgs boson in 2012 revealed the mechanism by which particles acquire mass, a field woven into the vacuum itself. Yet the Higgs also carried a warning. Its measured mass suggested that our vacuum might be metastable, perched precariously like a ball in a shallow valley. The LHC's data hinted that emptiness was fragile, capable of collapsing into a deeper void. If so, then the universe's birth and fate were not anchored in permanence, but suspended by chance. Cosmic surveys extended the reach further still. Telescopes like Hubble, Euclid, and now the James Webb Space Telescope, JWST, scanned the earliest galaxies, peering back to within a few 100 million years of the Big Bang. Each faint light was a fossil, its structure a test of cosmic models. Did inflation seed galaxies in the patterns we observe? Does dark energy act as a constant pressure, or does it evolve? The answers were written in the clustering of galaxies, in the bending of light by gravity, in the web of matter stretching across billions of light years. Quantum experiments joined the search. Ultra-cold atom interferometers tested the limits of uncertainty. Laboratories studied vacuum fluctuations, the restless dance of particles in emptiness, hinting that nothing was never silent. The Casimir effect, a measurable force arising from the energy of the vacuum, proved that even in the laboratory, a void is not void. The same principles that pull metal plates together whisper of a universe where nothingness carries weight. Together, these instruments transformed speculation into pursuit. Each tool sought a fragment of the answer, a clue to what nothingness might mean. The microwave background mapped the infant cosmos. Gravitational waves promised to reveal their earliest heartbeat. Particle colliders probed the fragility of the vacuum. Telescopes charted the first galaxies. Quantum experiments weighed the energy of emptiness itself. And yet, each advance carried a paradox. Planck confirmed inflation's traces, but not its mechanism. LIGO caught black holes colliding, but the primordial hum of creation remains hidden. The Higgs revealed the vacuum's instability, but not its cause. Webb sees galaxies sooner than expected, hinting that our models may miss some crucial chapter. Science had sharpened its tools, but the veil remained. Still, progress was undeniable. The very fact that nothingness could be tested, that questions once confined to myth and philosophy could be framed in detectors and datasets, was a triumph of the human mind. For the first time in history, humanity was not only imagining how something could emerge from nothing, it was building instruments to measure the silence itself. But the paradox deepened as precision grew. For the closer science came to describing the void, the less void it appeared. The vacuum carried energy. Fluctuations left fingerprints. Gravity rippled. Galaxies bloomed where nothing once reigned. The silence of origins was louder than expected. And in that noise lay the most haunting question of all. Not whether the universe began, but whether it could ever have failed to. The tools of science, in their triumph, had not banished mystery, they had magnified it, giving nothingness a texture, a weight, a sound. What began as a philosophical abyss had become an experimental frontier. The deeper paradox was now clear. The more we tested nothing, The more we discovered, it was never empty. The search for nothingness did not end with the familiar instruments of astronomy. It expanded into a global network of experiments, each pushing at the frontier where physics fractures into paradox. If the question was how something could emerge from nothing, then every tool became a probe into the silence. Every particle, every photon, every vibration of space-time, a messenger from the unknown. One of the boldest attempts to hear creation's echo came from the study of pulsars, dead stars that spin with clock-like precision, their beams sweeping across Earth like cosmic lighthouses. By measuring the timing of these signals across vast arrays, scientists hoped to detect the stretching and squeezing of space caused by gravitational waves too slow for LIGO to catch. These nanohertz waves, if found, could trace their origins back to inflation itself, to the turbulence of space-time in its first instance. In 2023, pulsar timing arrays announced tantalizing hints of such a background. If confirmed, it would mean that the void had spoken, its vibrations etched into the ticking of dead stars. Elsewhere, enormous detectors buried deep underground or submerged beneath ice searched for neutrinos, the ghost particles that stream through matter almost without a trace. These messengers, born in nuclear furnaces and cosmic collisions, also carry whispers from the early universe. If detected from primordial origins, they could reveal conditions even before the release of the cosmic microwave background, a window into the first second of time. Observatories like IceCube in Antarctica transformed the Earth itself into a detector, turning solid rock and frozen water into canvases for cosmic ghosts. In their silence lay the potential to glimpse the state of matter when the universe was still an infant. Quantum laboratories carried the paradox into scales no telescope could reach. Researchers cooled atoms to billionths of a degree above absolute zero, creating quantum states that magnified the tiniest fluctuations. These atom interferometers were designed to test whether gravity itself obeyed quantum rules. If spacetime is quantized, its discreteness might appear as subtle noise, an irreducible jitter in the vacuum. Detecting such a signal would mean that the fabric of reality is not continuous, but woven from quanta, a discovery that could erase the singularity and rewrite the meaning of nothing. Cosmology, meanwhile, deployed its most ambitious eyes yet. The James Webb Space Telescope had already peered into the dawn of galaxies, revealing structures earlier than expected, hinting that cosmic evolution may have raced ahead of theory. Future observatories, the Nancy Grace Roman Space Telescope, the Square Kilometer Array, next-generation X-ray and gamma-ray missions, aim to map not only galaxies, but the dark scaffolding that holds them. Each new observation tested inflation, dark energy, and the vacuum's hidden properties. If galaxies appear too soon, if clustering deviates from models, then the fingerprints of something beyond the Big Bang may lie in their patterns. Particle physics pressed further into the vacuum's secret architecture. The discovery of the Higgs had revealed one thread, but many suspected more: supersymmetric partners, extra dimensions, unknown fields. Though elusive, their existence could explain why the vacuum has the energy it does, why inflation occurred, and why the constants of nature take their improbable values. The vacuum's fragility, suggested by the Higgs mass, left open the possibility that accelerators or their future successors could uncover evidence that our nothing is perched above deeper layers of law. The rise of quantum computing offered another, stranger tool. By simulating quantum systems too complex for classical machines, physicists hope to mimic conditions impossible to recreate in laboratories. Simulations of black hole evaporation, entanglement networks, and holographic dualities hinted that space and time might indeed emerge from quantum information. In these machines, fragile and error-prone, was the possibility of glimpsing the pre-geometric state from which space-time itself may have condensed. But even as tools multiplied, the paradox grew heavier. For every observation that confirmed the Big Bang, another revealed its incompleteness. Planck's precision confirmed inflation's echoes, yet no definitive detection of primordial gravitational waves emerged. LIGO and pulsar arrays revealed ripples, yet the faint hum of the earliest universe remained elusive. Neutrinos streamed through detectors without revealing their origins. The Higgs told of fragility, but not of cause. Webb showed galaxies blazing early, but not the mechanism that lit them. It became clear that the paradox might never collapse into a single answer. Instead, science had entered a new phase, not the pursuit of one theory, but the weaving of many. Observations carved boundaries, instruments revealed textures. Each experiment defined what nothingness could not be, narrowing the range of what it might mean. The tools themselves became a philosophy. To weigh the vacuum is to admit that emptiness has weight. To listen for primordial waves is to admit that silence vibrates. To chase neutrinos through ice is to admit that invisibility leaves tracks. To simulate space-time on fragile qubits is to admit that geometry may be born from information. The scientific method had reached the horizon of beginnings, yet instead of turning back, it had built instruments to live there. For the public, the paradox of nothing might seem abstract, remote, untouchable. But the detectors are real, their discoveries tangible. When LIGO's arms stretched under the passing of spacetime's ripple, when Planck's detectors mapped the infant cosmos, when Webb caught the faint glow of galaxies older than theory predicted, humanity stepped into dialogue with creation itself. Nothingness was no longer a silence outside our reach. It was something that could be measured, mapped, perhaps even understood. And yet, humility lingered. No instrument could reach before time. No telescope could pierce beyond the horizon of our universe. The paradox remained, retreating like a mirage each time it was approached. The tools had not ended the mystery. They had illuminated its depth. The story of ongoing testing was not of triumph, but of persistence. The willingness to ask, again and again, if nothing can ever be real. It was a reminder that science, even at its peak, is not the conquest of truth, but the patient drawing of its outline. The edge of knowledge may never dissolve, but each experiment pushes it further, revealing not answers, but questions that are sharper, richer, and more human than before. And so the investigation continues, with telescopes that stretch sight to the dawn, with detectors that hear the tremor of spacetime, with colliders that peel back the vacuum's disguise, with computers that simulate impossible states. In each, the hope remains that somewhere in the noise of the void, the secret of beginnings waits to be heard. For in the end, the paradox of nothingness is not a wall, but a mirror. The more humanity builds to probe it, the more it sees itself, a species unwilling to accept silence, reaching into the abyss, not to banish the dark, but to listen for the faint echo of why there is something rather than nothing. To stand at the edge of nothingness is to stand at the edge of thought itself. For all the instruments we have built, for all the theories we have conjured, the abyss before creation remains an enigma that resists both equation and imagination. And yet, within that resistance lies a strange gift. The mystery of nothingness does not diminish us, it magnifies us, inviting us to see existence not as given, but as precious. Philosophers have long asked why there is something rather than nothing. To physics, the question has become sharpened, not why there is something, but how something could arise when nothing seems impossible to define. Every attempt to strip the universe to its silence reveals instead a hidden music. Vacuum energies, quantum fluctuations, entanglement webs, inflationary fields. The void is never empty. The silence is never still. Perhaps the paradox is not that something arose from nothing, but that nothing, in the deepest sense, may never have existed at all. This realization carries a profound weight. For if nothing is unstable, if voids shimmer with possibility, then existence is not an accident perched on a knife's edge, but a natural flowering of what cannot help but bloom. Creation becomes not a miracle, but an inevitability. Not a singular spark, but the unfolding of a law as ancient as potential itself. The question then shifts, not why the universe began, but why it began in a way that allows us to ask the question at all. Here, philosophy and physics meet. The anthropic principle, dismissed by some as resignation, becomes in this light a mirror to our own fragility. We are here because our cosmos allows it. The constants, the fields, the energies align not for purpose, but for possibility. And yet, the improbability of it all strikes us as profound. Out of the landscape of possibilities, we inhabit this one, a universe where stars burn long enough for life, where chemistry knits complexity, where minds arise that can wonder about the abyss. To call this a coincidence may be true, to call it meaningless may not. Meaning is not only in origins, it is in awareness. That we can ask about nothing is itself extraordinary. If the void had remained silent, there would be no galaxies, no atoms, no beings to wonder. That there is something, anything at all, is already a triumph over silence. That something contains us, fleeting sparks of consciousness, is more astonishing still. The reflection deepens when we consider time. If time itself began with the Big Bang, then to speak of before is to misuse language. But the human mind rebels against such limits. We are creatures of narrative. We demand beginnings. To say there was no before is to step beyond intuition, into a logic that feels more like poetry than mathematics. And yet, perhaps this is fitting. For beginnings may not be events, but transitions, phase changes in the hidden fabric of law. Just as water turns to ice without a singular moment, perhaps being turns to existence without a singular cause. Nothingness dissolves not in explanation, but in transformation. The shock of this idea is humbling. We are accustomed to answers, to planets orbiting by gravity, to diseases explained by germs, to atoms described by quantum mechanics. But here, at the threshold of the void, answers recede. The more we learn, the more we realize that the ultimate origin may be unreachable, not because we lack intelligence, but because reality itself may not permit such a view. The horizon of nothingness is like the event horizon of a black hole, a boundary not of curiosity, but of possibility. Beyond it, we may never see. And yet, this is not defeat, for the inability to see beyond does not erase the grandeur of what lies within. The night sky, filled with galaxies receding into the dark, is not diminished because we cannot trace its beginning. The mystery makes it richer. The fact that we can even approach the question that we can test the silence with telescopes and detectors, is itself a victory of the mind over ignorance. Perhaps, then, the true gift of the paradox is perspective. To contemplate nothingness is to remember that everything we cherish, the warmth of the sun, the laughter of friends, the curve of oceans, the glimmer of stars, exists against a backdrop that might have been silence. Our universe did not need to be, yet it is. We did not need to exist, yet we are here. Every breath is framed by the question of absence. Every moment is illuminated by the possibility that there might have been none. And so, philosophy bends toward gratitude. Not gratitude in a religious sense, though some may find it there, but gratitude in the sense of awe, a reverence for the fact of existence itself. To live is to stand as witness to a cosmos that could have been still, yet chose to sing. To wonder about nothingness is to realize the miracle of presence. In the end, science and philosophy may not resolve the paradox. They may never fully explain how something came from nothing, or whether nothing ever truly was. But perhaps that is the point. The value of the question is not in its answer, but in its pursuit. The mystery of nothingness stretches the human mind to its limits, demanding that we hold contradiction, embrace uncertainty, and dwell in awe. The abyss before creation may never yield its secret, but in gazing into it, we discover something else. Not an answer, but ourselves. Fragile, fleeting, curious beings, daring to ask why there is something rather than nothing, why the silence broke into song, why existence glimmers against the void. This is the paradox's final gift, that in searching for nothing, we find the meaning of everything. If the beginning of the universe remains hidden behind a veil of paradox, then perhaps the truest reflection is not in what we know, but in how we stand before what we cannot. Nothingness has become the mirror in which humanity sees the limits of its reach and the boundlessness of its wonder. Black holes embody this lesson in their very form. They are cosmic riddles, devourers of light, guardians of horizons, keepers of secrets we cannot read. At their heart lies the singularity, the same point of infinite density that haunts the origin of the cosmos. To study them is to face the same abyss that greets us when we ask of beginnings. We throw matter into their depths, we send equations to their horizons, but the story always ends in silence. And yet, in that silence, physics found its boldest ideas. Entropy painted on horizons, information preserved in surfaces, holograms encoding hidden volumes. Black holes taught us that nothingness is not absence, but encryption. Not void, but veil. The same may be true of the universe itself. For our own lives, the lesson is no less profound. Each human being, like a star, is born, burns, and fades. We emerge from silence, carry for a time the light of awareness, and return to silence. The question of nothingness is not distant, it is intimate. To wonder how the universe began is also to wonder how we began. To ask what remains when time collapses is also to ask what remains when we are gone. In the abyss of nothingness, we glimpse our own mortality. But mortality, like the vacuum, is never empty. Every moment of awareness is an island carved from silence, a brief flame against the void. Just as the universe arose, inexplicably, impossibly, so too does each life. And just as cosmology cannot say why there is something rather than nothing, so too can no philosophy fully explain why there is you, here, now. It is not inevitability. It is a miracle, a fragile, fleeting miracle suspended between two eternities of silence. The paradox of nothingness deepens when turned toward time's arrow. Entropy drives the universe toward disorder, yet from its early low-entropy state came galaxies, stars, and life. Order flowered in defiance of inevitability. Our very ability to ask why there is something rather than nothing is a product of that improbable flowering. In this sense, the paradox is not just cosmic, it is personal. Out of all possible histories, out of all potential silences, you exist. And so reflection circles back to gratitude. Not the gratitude of certainty, but the gratitude of astonishment. We may never know if nothing ever truly existed. We may never know if time has cycles, if universes bloom eternally, if inflation spawns infinities, or if space-time is woven from quantum threads. But we do know this: the universe exists, and within it, so do we. That is enough to turn silence into song. In the halls of science, the pursuit continues. New detectors will listen for gravitational waves born in the first trillionth of a second. New telescopes will peer deeper, capturing galaxies as faint as whispers. New theories will attempt to stitch relativity and quantum mechanics into a seamless cloth. But even if no final theory comes, even if the paradox of nothingness remains, the pursuit itself is meaning. For in seeking answers, humanity defines itself. Not as conqueror of mysteries, but as companion to them. Perhaps the truest resolution is that the universe is not obliged to give us beginnings we can understand. Perhaps nothingness is not a puzzle to solve, but a horizon to dwell upon. In this horizon, we learn humility, that the cosmos is not scaled to our intuition, that its origins do not conform to our need for causality. But in humility, we also learn wonder, that we can still reach across billions of years, across equations and paradoxes, and catch glimpses of what lies just beyond comprehension. In the end, to ask whether nothing ever existed is to be human. It is to admit both our smallness and our greatness. Small, because we are finite creatures in a vast and ancient cosmos. Great, because we dare to ask of existence itself. Our ancestors once looked at the stars and saw eternity. We now look and see a beginning, a silence that broke into fire. That vision may never be complete, but it has already reshaped who we are. And so, the story closes not with certainty, but with reflection. Before the first atoms, there may have been silence. Before the first moment, there may have been nothing. Or perhaps silence and nothingness are illusions, masks worn by a reality too deep to name. Either way, what matters is not the veil itself, but that it lifted just enough for us to be. Everything we are, every galaxy that spins, every song ever sung, every dream ever dreamt, is framed by that lifting. Against the possibility of nothing, we are something. Against the horizon of absence, we are presence. Against the silence, we are a voice.